Next, we want to look at identifying both horizontal and what we'll introduce as oblique asymptotes of a rational function. In the picture on the left, the graph on the left, we have the rational function that we considered back a few examples ago, which has a vertical asymptote at x equals -2 and a horizontal asymptote at y equals 1. Again, horizontal asymptotes, and it'll be the same for oblique asymptotes, deal with the behavior of our function at the extreme values for x, as it's either approaching positive or negative infinity. We can see from the graph on the left that as our values for x get larger and larger and larger and larger, what's happening is our function is going to keep getting closer and closer to that line y equals 1. And as x approaches negative infinity, keeps getting smaller, we're also approaching that line y equals 1. So horizontal asymptotes tell us what the end behavior of our function is like, and oblique asymptotes do the same. With the graph on the right, we have two vertical asymptotes, one at x equals -7 and one at x equals +7. And then this graph has an oblique asymptote, meaning instead of a completely horizontal asymptote, we have a line that serves as that asymptote and depicts or helps us understand the end behavior of our function. So as x keeps getting increasingly large, our curve is going to keep getting closer and closer to this line y equals x, and the same thing is going to happen as x approaches negative infinity. We'll keep getting closer and closer to that line y equals x. So oblique asymptotes give us the same sort of information. They tell us about the end behavior, but rather than being a completely horizontal line, we have a line with some slope. So in order to find those oblique and horizontal asymptotes, we consider what's happening to our function as x approaches positive or negative infinity. So if we have some given rational function, a sub n times, x to the n power plus a sub n minus 1 times x to the n minus 1 power plus however many terms we have, down to just a constant term, over some other polynomial function, b to the m times x to the m plus b to the m minus 1 times x to the m minus 1, on and on for however many terms we have, until we get to that constant term. What we would say is that if we consider x approaching both positive and negative infinity, what we consider is our function approaching the dominant term or the leading term of both the numerator and denominator. So essentially whatever this leading term is in the numerator and denominator of our function, as x gets increasingly large, those terms are going to increase so much faster that our function is essentially approaching a sub n x to the nth power over b sub m x to the nth power. Or essentially what we're saying is all other terms drop out or become less influential to the function value, and we just focus on those two leading terms. When we consider just the leading term for the numerator and denominator of our rational function, there are 4 different outcomes we can encounter. First outcome or first case would be the case where n is equal to m, meaning the leading term in the numerator and denominator have x raised to the same power. So that means we would have a times x to the nth power over b times x to the nth power. So x over n divided by x over n would cancel, which would leave us with just a over b. If that's the case, then what we have is a horizontal asymptote defined by the line y equals a over b, so whatever those coefficients reduce down to. In case 2, we have m greater than n, meaning the exponent for x in the denominator is larger. So if that that exponent in the denominator is larger, we would say that our function is going to be approaching 0. As a few examples to help understand this idea, we could consider something like x squared over x cubed. So that exponent in the denominator is larger. This would reduce down to 1 over x, and as we plug in larger and larger values for x, or smaller and smaller values as we plug in extremely positive or negative values, we'll get values that keep getting closer and closer to 0. You could verify that with your calculator. Or similarly, if we considered x to the 8th power over x to the 20th power, this would reduce to 1 over x to the 12th. As we plug in extreme values for x, we would keep generating values closer and closer to 0. So in this case, we would end up again with a horizontal asymptote. In this case, occurring at the line y equals 0. So those are our two cases where we'd end up with a horizontal asymptote. If we end up with a case where n is equal to m plus 1, meaning our expression in the numerator is a times x to the m plus 1, and our expression in the denominator is bx to the m, our variable components would reduce down, so we would get ax over b, and this would tell us what we have is an oblique asymptote with the equation y equals mx plus b that we need to determine through long division. So specifically, again, what we're looking for in this case is a case where our leading terms reduce and we have x to the first power. This is different than the case where we have m greater than or equal to m plus 2. In this case, we would have a times x to say the m plus 2 power over bx to the m. This would reduce to a to the m squared over b, which would tell us that we have no horizontal or oblique asymptotes. Instead, what we'll have is n behavior determined by that power function left over. So in this case, if we ended up with, sorry, that should have been an x squared, not an m squared. If we had something with x squared, then we would have something with n behavior pointing up at both extremes. So the difference here is we're looking for, in case 3, x raised to the first power, and in case 4, x raised to any power larger than 1.